Okay, so before we get to Hessian matrices, let me start. Oh yeah, one thing I found out that I made a bug in numbering the lectures on YouTube, but now I fixed it. So it should be all good. So this one should be officially number 22. If you are, I guess you are not the ones who are following it, but the ones who are not here are hopefully following it on YouTube. So on Wednesday there won't be any class. I'm again reminding, we already discussed that. The project number 5 is due on Wednesday, I think midnight as usual, right? And there won't be any new homework because it's the Thanksgiving week. There will be another one for the next week, and I think that will be the last one. And there's actually not so many classes left, right? It will be like 2, and there will be 1 Monday, be done. So just do this, then we will do the page rank on Monday, and then we'll do SVD, and then we'll be done. And then will be, well, then there will be final exam, and then we'll be done. Okay. So let me remind you, what did we talk about last week? So I guess the most important result was that if I have a symmetric, square symmetric matrix, then I always can find a full set of real eigenvalues. So I mean, it's always a full set. In the special case of a symmetric matrix, they are real. And most importantly, I guess I could put exist eigenvalues. And V1 up to Vn, this would be Rn eigenvectors. And I guess I don't have to remind this that what it means is AVI equals lambda I VI. And moreover, these eigenvectors are orthonormal. So that's the special thing, that's the luxury we have with symmetric matrices, that we get eigenvalues which are real, and the corresponding eigenvectors can be chosen so that they are orthonormal. And this led us to the classification of all symmetric matrices. And I would like to elaborate on that a little bit more today. So that we had these 5 cases, right? So the first one was that A is positive. This is a really horrible thing to sit on. It's positive positive definite. Positive definite. And we defined it by saying that that means that all of the eigenvalues must be strictly greater than 0. Okay? And what I showed you, I think the last time, is that this is equivalent. This can be proven. This was the definition, and we can equivalently prove an equivalent condition that for every non-zero vector, or n, x is non-zero, we have xtax greater than 0. Okay, just like this. That's an equivalent condition for that. And I think we discussed the proof the last time. It's not very difficult. Okay, then the other cases was that A was positive. Let me write it. Positive semi-definite. What do I need to change? What's the only thing that changes if I go from positive definite to positive semi-definite? So this all stays the same. What changes there? Yes, it will be greater or equal than 0. And guess what changes here? Oh, is it refocusing? Let me lock it. All the changes, this whole stuff is the same. And guess what changes here? Greater or equal. Yeah. I guess I don't have to put this x non-zero, right? Because then for x0 this would also be true. So that's just like a technical detail here. Okay, the third case was negative definite, right? A is negative definite. So again, same idea, right? So what does that mean? That means that for each of the eigenvalues it has to be strictly negative, right? And again, you can prove fairly easily that that means that for every non-zero x, the quadratic form xtax will give you a negative number, okay? And I guess it's not very hard to guess what's going to happen in the negative semi-definite case. Well, I think you guessed it by now. That's this. And here we will get xtax less than or equal than 0. Okay. And there's a funny special case, number 5. What was that? Anybody remembers that? So the funny special case that A is indefinite. It's actually quite important. It's just some sort of corner case. That means that there exists one eigenvalue number I, another number j, such that the lambda I is strictly greater than 0 and lambda j is strictly less than 0. Okay, so there are both positive and negative eigenvalues. Here I said that they are real. Well, that's cool, but they can be positive or negative, right? And if it's mixed, it means the matrix is indefinite. Well, and guess what it means here? Here it means that if I'm looking directly at the values of the quadratic form, that means that there exist vectors x and y, such that for if I do x, I will get a positive number, and for y, I will get a negative 1. Okay? And this is all of these are basically, the proof of all of these properties is straightforward and goes from spectral decomposition. We discussed that the last time, right? So no need to reiterate that. So this is basically a recap, okay? What I wanted to point out that there is like a cool corner case. You can think about a funny case when n is 1. So it's actually sort of fun to think about it. So if n is 1, that means we have a 1 by 1 matrix, aka number, okay? So what does this mean if I have a 1 by 1 matrix? So I guess I could write it like this, right? What is its eigenvalue and eigenvector? It should be something really simple, right? So what it is. So I set eigenvalues and eigenvalue lambda corresponding eigenvalue lambda I corresponding to eigenvector vi has to satisfy this property, right? Hmm? So what is itself? A11. Is what? A11, that's correct, but what is A11? There's only I guess you're talking about the eigenvalues. Yes, correct. So indeed, yes. I mean, it's as simple as writing this, right? So basically the eigenvalue is going to be A11 itself, okay? And the eigenvector, what's going to be the eigenvector? You got the eigenvalue right. That's just the number itself. 1, yes. Or 2. Or 3.17, right? It doesn't really matter as long as it's not 0, right? Because if okay, let me put here 1, right? And of course, this is the same. But the way you need to look at it, that this here is an eigenvector, here is an eigenvalue, here is an eigenvector. So everything is cool, right? So in the 1D case, so why do you think I bother about this sort of silly 1D case at all? Well, to show you that this positive, negative, semi-definite, these definitenesses, they basically generalize the notion of positive, non-negative, negative, and non-positive number. Okay, so how is that? Well, what it means positive definite for this matrix? Well, that means that the number is positive, right? Positive semi-definite means that the number is greater or equal than 0. This is what people usually call non-negative. Negative definite, that means that the number itself is negative, right? It's below 0, and semi-definite means is less than or equal than 0, okay? There is no such thing as indefinite in the 1D case. That can only happen in 2D and higher dimensions, okay? But the point of this is that this basically is a natural way to generalize the concept of a positive number or non-negative number, all these 4 cases, right? Okay. Oh yeah, here is a different type of geometric interpretation of positive definiteness. Let me try to squeeze it in here. Interest of saving paper. If you look at these properties, what do they? You can think about them geometrically. What do they mean? So if I have xtax greater than 0, okay, and this should hold for every x which is non-zero. So let's talk about positive definiteness for now, okay? So how can I interpret this geometrically? What does this mean? Well, one way I can look at it is as a dot product of x and ax, right? So let me write it like this. I guess it's sort of silly, but x dot ax, right? I can imagine that I like first do a times x and then I dot product it with x. Well, that's one way I can certainly be looking at it, right? So what does it mean? Let me draw a picture. If I pick any x non-zero, okay, that means the A matrix maps it somewhere. Okay, if I look at the matrix as a transformation of a vector, okay? If it was a zero vector, it would just map it to zero, so it would not be very interesting. But if I have a non-zero vector, that maps it to someplace interesting, hopefully. So for example, if it maps here, so if this is my x, and this is where the matrix A maps it, that's my AX. And here what I'm looking, the XDAX, that's just the dot product of x and AX, okay? And here I want the dot product to be positive. So geometrically, what does it mean for the dot product to be positive? Where AX must be on this picture so that the dot product is positive? That's, I guess, what we started with, right? Like lecture 1.
On the right side?
Yes, so if I, exactly. So if I create a hyperplane such that its normal is x, I mean, it's just a line in 2D, right? But this would work in any dimension, just that I cannot draw it in any dimension. So that means that the AX has to be on this side, on this like on this half space, right? If the AX happen to be here, then the matrix A can no longer be positive definite. Okay, that's sort of like different way how you can think about that. Sometimes might be useful. All right, let's take a look at one quite important application of all this business. Okay, so far we talked about quadratic forms, right? And the last time I discussed that these things have like very direct geometric interpretations in terms of quadratic forms. Quadratic forms were just like functions from Rn to R, which were purely quadratic. Okay, and I think I told you that in the positive definiteness means it's convex. Okay. The 2 means the semi-definiteness, it's weakly convex. This one is concave, and this one is weakly concave. And this one is neither, the indefinite. That means this is a saddle point, okay? Now the importance of this comes from the fact that this applies not just to quadratic functions, but you can actually apply similar type of analysis to absolutely arbitrary functions. And that is when you look at Hessian matrices. So let's take a look at that now. So we talked about, so maybe like let me motivate that. So we talked about derivatives, right? All you need to, I think, okay, some people might disagree, but I think all you need to remember from calculus is that derivatives are linear approximations, local best fit linear approximations of a given function, right? I was drawing many times like this. If I have some function and I'm interested in some point here, and the function may be complex something, right? It can be arbitrarily complex, but you can always approximate it with just linear or affine function, because this might not necessarily be at 0, right? Maybe I'm some coordinates like this. So here there is some value, but once I translate myself to this value, then I'm just doing a linear approximation. Okay, that's the idea of a derivative. Now, sometimes this works just fine, but sometimes you are not happy with the approximation accuracy of just a linear function. Okay, sometimes you just need to do a little bit better approximation of the function than linear. Okay. And what you can do, and what's actually extremely useful, is to do second order approximation. So the linear approximation means taking first order derivatives, okay? And we discussed this many times, and you probably know that from other classes too. To do second order approximation means that you are finding the locally optimal quadratic function, the best fit quadratic function, okay? And that's exactly what leads to Hessian matrices, okay? So let's look at this this example, because that's where, again, symmetric matrices and all this positive definitenesses, that's where this shows up. So we will look at a 2D function f. Okay, so f is a function from R2 to R. Imagine, like, again, a height field. Okay, if this is my defining, it's my x and y. The function again assigns a height. And let's say that x and y are some important point and in the vicinity of the point, I'm interested in the behavior of the function, okay? So for example, if you are doing physics-based simulation, like I guess you are doing right now, right, with the springs, with the the stretchy rope kind of example. If you were doing 2D physics, I guess, then maybe this is like your current state, okay? And you want to see where the system will evolve in time. So you want to approximate the function at x and y, okay? So what you do multivariate Taylor expansion. So what does delta x and delta y means? Well, that means that some small displacement, okay? So delta x will be some number close to 0, delta y will be also something close to 0. It technically doesn't have to be close to 0. That's what this like approximately equal means, okay? So this approximately equal means this is equal as long as delta x and delta y is small, okay? There is more math to it, but I guess here we can just stick with this intuitive interpretation. And then what the second order approximation is, well, first you do the 0th order approximation, right? I guess, again, I like to consider extreme cases today. I said that the standard derivative type of thing is to do first order approximation, but you could also do a 0th order approximation, right? Just put there a constant. That would be even dumber approximation, right? Even simpler one. You don't even have to compute any derivatives, right? Just assume that locally the function is constant, okay? So that's this first term. That's the value there, right? That's the most obvious thing you would think about, right? Then the second term here, that's exactly the differential of the function. So it consists of a partial with respect to x and partial with respect to y, and each of them is multiplied by the small displacement delta x and delta y. So this is exactly the locally optimal linear approximation of the function, okay? And Taylor, I guess it was a dude, right, had the idea that we don't have to stop there, but we can keep going. And we can create more accurate approximations if we take higher order derivatives of the function. So that's exactly this, and that's the term we will focus on right now. That's the second order term. So let's take a look what's here. So first of all, there is the 1 over 2. If you know the Taylor polynomial business, you know that's 1 over n factorial, then n is the order of the derivative, right? But here it's just 1/2. Here it was 1 over 1, so nothing really happened there. So we have a second partial with respect to x. We have a second partial with respect to y. So this is multiplied with delta x squared, sort of makes sense, right? And this is multiplied delta y squared. And here we have a mixed term. So this is the mixed partial derivative. So this is f differentiated with respect to x and then with respect to y. You should know from calculus, multivariate calculus, that it doesn't matter which way I differentiate. It doesn't matter if I first differentiate by x and then by y, or first by y and then by x. I have to get the same value either way, okay? And it's also multiplied by delta x and delta y. So if you look at it again, this is the constant term, this is the linear term, and this is a quadratic term, okay? And here we sort of tied back to linear algebra. So the constant term, that's just a number, right? The type of this is just a real number. Can be negative, right? But that's all it is. Here I have the gradient of the function, okay? So this is a 2x1 matrix here. So this is the gradient of f. Here is just the delta x and delta y. I just made a vector out of it. No big deal, right? So this is exactly the first differential term I've written in like matrix notation. It's a 2x1 matrix by 1x2 matrix times 2x1 vector. And here, this is the interesting thing here. This is the quadratic term written using a Hessian matrix. Okay. So what does the Hessian matrix? The Hessian matrix is a matrix of second derivatives. Okay. So on the diagonal there are the second partial derivatives. So here you have the second partial with respect to x, here is the second partial with respect to y, and here you have the mixed ones, okay? Because it doesn't matter if I differentiate first with respect to x and then with respect to y, then this matrix is symmetric, okay? And we are, now you can see why this is a good time to bring this up, because all that we said about symmetric matrices applies to Hessian matrices, okay? Because they are real symmetric matrices. And turns out that it will be useful, or we can learn something about the function by reasoning about the definiteness properties of these matrices. And we can actually do even more by looking at this Hessian matrix. So this is the Hessian matrix. I guess it's written here, right? Yeah, so this, I guess this could be called the Jacobian. In the 1D case, you could also call it gradient, but if this was a function going to some Rm, then you would probably want to call it Jacobian. So the Jacobian means first order derivatives, and the Hessian means second order derivatives, okay? And what this thing does, it gives you the best, if you put it all together, it gives you the optimal, locally optimal quadratic approximation, okay? So basically, if I can stick with this example, it's already a little bit cluttered. The question I'm answering here is, if at this point, x, I wanted to find the optimal quadratic function that will approximate my function as closely as possible in the small neighborhood of x, then I will get some quadratic function, would be sort of close to it, and would look like this. Question, yeah?
So if I can go further, right?
Yes, absolutely. You can keep going. And then yeah, you can go to third, fourth, and so on. It's easy in the 1D case, right? You have seen, I think I have shown you the Taylor polynomial, right? Like for the exponential, it was exactly the same idea, right? I mean, the 1D case would be, so if this was x plus delta x, then this would be fx plus, oops, where did that come from? Plus the derivative of f at x times delta x plus 1/2 second derivative delta x squared, and then I would do 1 over n factorial and the derivative of f at x delta x to the power of n. Okay. Now in the 1D, that's cool, right? In the multivariate case, in the multidimensional case, that gets a little bit funny, right? Because what would you get here? So this is a Jacobian, this is a number, this is a Jacobian, this is a vector, right? Or just a matrix with one row. This is a Hessian, right? So this is a 2x2 matrix here. What do you think would be the next term if you wanted to go to third order approximation?
3 by 3.
No.
3 by 3 by 3?
Huh?
3 by 3 by 3?
No 3. This is just 2D. I mean, we are talking about the 2D function. 2 by 2 by 2. 2 by 2 by 2 tensor. Okay. So the generalization of all this business is tensors. So we won't really go there. That's a little bit advanced linear algebra. If you are in mechanical engineering, you will probably have to make friends with tensor at some point. It's like in elasticity, they are important, but I don't think this is the point yet. Yes, so if you wanted to continue, you would have to go to like higher order tensors. Even the notation then gets funny. Yeah, so let's not go there now. Okay. That's a good question. Any other questions here? Oh, I mean, of course, this is essentially like entire calculus, right? So I don't want to do entire calculus here. What I want to do is to tell you some characteristics of the function which you can read from the Hessian matrices using the linear algebra tools we have discussed. Okay. So as I said, it's a real symmetric matrix, right? Of course, all the numbers are real. It's symmetric. So we can, so all what we said before, all this stuff applies to it, okay? So they have real eigenvalues and orthogonal eigenvectors, okay? And here is the interesting thing. So I guess here you can notice from this expansion, you can notice one thing. This linear term is in a sense stronger than the quadratic term. Okay, what do I mean by stronger? Well, this approximate equal only holds for small delta x and delta y, right? Like imagine like 0.001. Depends really on your resolution, right? But the idea is it needs to be small compared to whatever x is, okay? So this linear term is stronger in the sense that if delta x is small, so let's assume that delta x is like 0.1, then delta x squared is super small, right? So this linear term is like if they should compete, so this will have like a smaller contribution than this term typically, okay? But an interesting thing happens. If the first derivatives are 0, okay? Because if the first derivatives are 0, both of the partials are 0, then this term falls out, right? This term that's always going to be there. There is no going away from that, okay? So if this term falls out, that means that the locally optimal approximation is flat, okay? So that means there is something interesting going on with the function at that point, right? Because locally, if you are just fitting a plane locally, it's a flat plane. Okay, it's like in the 1D case, it's like this, right? It's not like this. It doesn't have a slope. It doesn't have a gradient. It happens to be flat. Okay. And in that case, the Hessian becomes all of a sudden very important because it tells you what exactly is going on at the point xy we are looking at. Okay. We already know if the first derivatives are 0, there is something going on, but we don't know what exactly that is. Okay. But you can tell that by looking at the Hessian matrix. I don't know if you had this in calculus. Maybe you did.
What? It's like double derivative of the 1D case, right?
Yes. This is the Hessian is directly generalizing the second derivative, right? I guess I could just say in the, or I might have even said it, right? In the 1D case, there is no matrix. There is just, I guess we are, you know what? We are back to this 1-by-1 matrix case, right? Everything is cool there. And if it was like a 3-dimensional or a million-dimensional function, that would be the same. We would just have if it was n-dimensional, he would have n-by-n Hessian. Okay? So if it's a 1D case, we have 1-by-1 Hessian. So here we have just like the second derivative of f with respect to whatever the parameter is. Okay? But the cool thing is that the Hessian, because it's a nice symmetric matrix, it tells us what is going on there in any dimension. Okay? If it's million, that's fine. So, and what is the key? It's to look if it's positive definite, negative definite, or indefinite. If it's positive definite, we are dealing with a local minimum. Okay, let's think for a second why local minimum. Because if it was positive definite, we said it's a bowl-shaped thing, right? Which means it's a convex function. Okay, well that means that at the point x and y, because the first derivative there was 0, I guess I could just draw something like this. Like in the 1D case, it would be this. In the 2D case, it would be like a rotated ball. In 3D and so on, it's harder to imagine, but it's still the same idea. Here is my point x. Okay. So indeed, if it's positive definite, it's a local minimum. If h is negative definite, that means that minus. That if I flip the function, it would be positive definite. That's the opposite case, right? That's a local maximum. And the interesting thing which does not happen in 1D, it happens only in 2 and more dimensions, is the case when the Hessian is indefinite. And that's the special case when there is neither a minimum nor a maximum. Because there are now 2 directions. Remember this characterization here. Wait, this one. Indefinite is the funny case where in one direction you will be locally convex. So maybe look at it like this. If you slice it with one plane, you will get a profile that will look like convex. If you slice it with another plane, you will get a concave one. Okay, so like really in a saddle of a mountain, right? In one direction you'll be going up on a mountain. In the other direction you'll be going down a valley. So that's actually no local extremum. That's like this sort of like false positive, right, of this first derivative test. You know that the first derivative is the way how you find local extrema, but you may also find not actual extrema. You can just find critical points, which actually turn out to be saddle points. Okay? So interestingly, you don't have to stop there, and if you are doing differential geometry, you will not stop there, and you will go way, way beyond this. So I will just give you, like, I guess, like a quick preview of differential geometry. What the Hessian tells you is some information about the local curvature of the surface at a point. Okay. So if you imagine, how would I explain that? Let's take a look at this. Oh, this is, by the way, also an example of a saddle point. Okay, do you see that nicely? Yeah, you do. So here is the point. Here is my xy. So this is a 2D function. Okay, this is from function from R2 to R. This is my point xy, which I'm really interested in for some reason. Maybe I found that the derivatives there are 0, which is quite interesting. So I'm looking at it a little bit more. And I can be analyzing the curvature of this height field at this point. Okay. I guess I should do a disclaimer that differential geometry would actually work, would be more general. What I'm talking about is just height fields like this. Differential geometry would assume that it's parametrized by something, and it gets a little bit more complicated. Then you need to show that's invariant to the parametrization, and so on and so on. let me just show it to you for curvature of a height field. Okay, in that case, it's simple. You can just get away with the Hessian matrix of the function directly. So what you can do is to reason about the curvature of the height field at this point. You can imagine you slice it with a plane. Okay, here is one plane, and then you can imagine you are rotating this plane. Okay, every time you slice it with this rotating plane, you will get some curve. Okay, just 1D function. Is that clear? Just get a 1D function. So I can compute directly the second derivative. Okay, which is the curvature there. Question? Oh, that's not good. I hope you know what? Let me delete something so the recording is not gonna fail. I was hoping this would come up when I was talking about data compression. I'm not good at this Mac stuff. I'm not sure where is it downloaded, saving it. Documents. Oh yeah, here it is. Okay, so I'll delete that. Okay, delete on my move to trash. Okay, that's it. Do I need to empty the trash too, or will it do it by itself? That didn't do it. Okay, I'm not really good at Mac. Oh yeah, there we go. Empty trash. That should take care of that. All right, sorry about that. It's a nice and portable, but doesn't really have a lot of hard drive. Okay, so what I was saying, yeah, right. I was saying that you can look at the curvature of this surface in any slicing plane. Okay, so as I'm rotating the slicing plane, I'll be getting different curvatures. Okay. It turns out that there are two extrema points. Like you can sort of see it here, right? Here, these two planes are the planes of what's called the principal curvatures, where you get the maximum and minimum curvature. Okay, that's what's called the principal curvatures, and I think that's what's elaborated on here. Well, not really. And the principal curvatures are their values. They are actually exactly the eigenvalues of the Hessian. Okay, so if your eigenvalues of the Hessian are lambda 1, lambda 2, eigenvalues of H, they are exactly the values of the principal curvature. Okay, and then there are some standard curvature measures. For example, the determinant of H, you know that the determinant of H, if I said that the eigenvalues are lambda 1 and lambda 2, the determinant is just lambda 1 times lambda 2. Okay, I'm in a 2D function. Okay, this is called the Gaussian curvature. And it's sort of smart, because if you think about it, what does it mean? It means that if it's positive definite, you get something positive. If it's negative definite, then both are negative, right? So you also get something positive, okay? And if it's indefinite, if one is positive, one is negative, just like in this case, right? This would be the indefinite case here. Then you get negative Gaussian curvature, okay? So the Gaussian curvature immediately detects if the point is local extremum or if it's a saddle point. Okay. Another important curvature measure is the mean curvature, which is 1/2 of trace of the Hessian, which is just the average of the two principal curvatures, lambda 1 plus lambda 2 divided by 2. That's what's called the mean curvature. And the mean curvature, that's what's related to Laplace-Beltrami operator on manifolds. But again, I don't really want to do like all differential geometry. I just wanted to show you this curvature of a height field as an example where a Hessian matrix would be interesting thing to think about. Okay. All right, the next thing, this is what we already talked a little bit about. Those are the anti-symmetric matrices. So anti-symmetric or skew-symmetric, that means the same. Okay, somebody prefers to say anti-symmetric, somebody prefers to say skew-symmetric. Okay, one way you can look at it, they are the evil twin of symmetric matrices. I guess the better way to think about it is that they are the complement of symmetric matrices. Okay. And we talked about this skew-symmetric. So, okay, first, what does it mean? If I transpose it, I get the same matrix times -1. Okay? I have to flip the sign of all the elements in the matrix. Okay? And we talked about them before, right? Do you remember in what context? What were this anti-symmetric, skew-symmetric matrices good for? In the context of linear differential equations, right? And I showed you that they are closely related to something you know very well. To rotation, yeah. The skew-symmetric matrices are generators of rotation, if you remember that lecture from a couple of weeks ago. If you don't, it's recorded. But here I want to look at the algebraic properties, I guess. Now let's not do this again because we already done it. So first of all, it's trivial to realize that the diagonal elements must be zeros, okay? Because the transposition does not move the diagonal elements, so they must be equal themselves times -1. Well, there is only one number that's equal to itself minus 1, right? Times -1, and that's 0. So the diagonal has to be zeros. And then the matrix is symmetric, except that you switch whatever, the sign. Okay. In the 3×3 case, we related this matrix to a cross product, actually. Sort of cool. But that's not my point here. Here my point is that the skew-symmetric matrices are essentially a complement of symmetric matrices in the following sense. You can take any square matrix and you can split it into a symmetric and skew-symmetric part. What I mean by split, you can find a symmetric matrix and anti-symmetric matrix such that A can be written as a sum of the symmetric and anti-symmetric matrix. Okay, that's actually super simple. There is nothing special about it. All you need to do is this. Okay, so first of all, it's trivial to find out to verify that this is indeed equal to A, that this equality is true. That's because I have half of A here and half of A here. That gives me A, right? And you have half of A transpose minus half of A transpose, that gives me 0. So this is really just saying that A equals A. But look at this. A plus AT is certainly symmetric, right? If I take A plus A transpose and transpose the entire thing, what I'm gonna get? Well, I'm gonna get A transpose plus A, but that's of course A plus A transpose, right? So that's a symmetric matrix because transposition didn't change it. And what about A minus A transpose? If I transpose that, what's gonna happen? Well, I will get AT minus A, right? And that's nothing but minus A minus AT. So that's actually one of these skew-symmetric matrices, right? Because transposition did not change it up to negating it, up to multiplying every element with -1. Okay? So this is the symmetric part. I guess it's written. And this is the skew-symmetric. And this decomposition is that simple, right? Like we were talking previously about LU decomposition and QR spectral decompositions. All these there you have to do some sort of non-trivial computational routines. Here this is a joke, right? To split it like this. Yeah, so that's one way, and a different, like an algebraic way how you can think about skew-symmetric matrices, that they are what you need to add to a symmetric matrix to be able to do any matrix. Okay. The point of the quadratic forms was that there you don't need the skew-symmetric part, and here is why you don't need the skew-symmetric part in quadratic forms. Because if I make a quadratic form with a skew-symmetric matrix, if I compute xdxx for any vector x, I always have to get 0. It's actually a very fun thing to prove. Think about how would you prove it. I think I used to have, well. So remember, this is the quadratic form. So if I had a symmetric matrix there, I was talking about all these cases of positive definite, negative definite, and so on, right? And here I'm saying that if I put there a skew-symmetric matrix, it must be just always 0. Simple as that. Does anybody see a proof? It's actually a very simple argument. Similar argument to what I have done here multiple times already. Yep. That's certainly true, right? But why would that necessarily, the x can be whatever, right? Like x can be all ones, for example. So how could you guarantee that it will not pick up some non-zero thing? There will be some off-diagonal, like this one, right? This still has some off-diagonal elements. So how do we know that it all cancels at the end of the day? I guess it's tricky because the proof is so simple. Give you a second to think about it. Okay, so watch this. So what is XDSX? That's a number, right? My favorite 1-by-1 matrix, the best matrix ever. Well, this matrix has the property that if you transpose it, then you get the same thing, right? Then you get, let me write it like this, XDSX equals its transpose, because it's a 1-by-1 matrix. Transpose doesn't do anything, okay? But what if I work it out? Well, here I will get this, right? What is ST? Well, that's a skew-symmetric matrix, right? So this is minus XDSX, okay? Well, that's the same thing, right? Again, that's the same argument I made, or if you want me to put it like this, I can put this on the other side, so I can say 2XDSX equals 0. Well, this is a number. The only number which multiplied by 2 gives 0 is a 0. So that indeed must be 0. It's a very, very, very quick, very elegant proof. I guess it's a simple thing to begin with. Okay, let's look at optimizing a quadratic form, like an optimization example now. So we have a quadratic function. Let's start with a 1D1, then I will generalize it to ND. And we want to find its minimum and realize what type of minimum it is. Okay, so the usual thing you can do here is, well, let's do it this way. We can just compute the derivative, right, which will be 2ax plus b. And then we know that something interesting is happening when the derivative is 0, right? That's here. So that means that x equals minus b divided by 2a, okay? Well, it turns out that this fx, this general quadratic function in 1D, I can write, I can basically get rid of the linear term by centering the x around this point. Okay, let me, maybe it doesn't make sense. Maybe the math will make more sense. So x plus b divided by 2a squared. Let's take a look at this, okay? What I'm trying to do here is to get rid of the linear term. So we can again apply what we have learned about symmetric matrices. In this case, in the 1D case, it will be really simple. So if I do this, so let me work out this expression. So that would be ax squared plus 2axb divided by 2a, right? Plus a, and let me just copy this, b divided by 2a squared, okay? So what this is just ax squared plus bx, right? Plus, and I will just copy that. Okay. So this basically, the key thing here is that this generates me the linear term. Okay. So if I want to bring this to this form, or better said, if I want to rewrite the fx, which is ax squared plus bx plus c, using this, then I can just use this, x plus b divided by 2a squared. Okay. Then I have to add c back, and then I need to subtract this term here, this a b divided by 2a squared. Okay. The point here is that this is just a constant. Okay, so this is, I'll call it d. That's just another constant, right? It's A, B, and C. A, B, and C, they were just real constants which were given to me, and x is the variable here, okay? So I can further simplify this by introducing a substitution. I can just say that this will be y, so I will introduce a substitution that y will be x plus b divided by 2a, okay? So basically just shift the variable a little bit. And what I will get is that the f after the substitution, the f looks really simple. So it looks like this, ay squared plus d. Where a is a constant and d is a constant, there is another constant hidden in the substitution, okay? Well then, reasoning about extrema of this function, ay squared plus d, that's really, really easy, right? Because what are all the cases which we have there? All we need to look at, so the d doesn't matter if we are talking about minimizing or maximizing it, about what type of extremum is there. So the three cases that can happen there is, so this will be, let's say this is my d, that d doesn't really play pretty much any role, right? And you know that if the a will be positive, we will get something like this. So this is for a positive. The special case is when a is 0, because then it's not even a quadratic function, then it's just a constant function in this case. So this is the case of a 0, and if a is negative, it's pointing the other direction, okay? It's sort of obvious why that is, right? As y grows, then a goes up or down depending on the sign of a. So the point here is that a, again, tells us what exactly is going on at this critical point here, the b divided by 2a, okay? Because if a is positive, we have a local minimum. If a is 0, we don't have anything. That's the special degenerate case. And if a is negative, we have a local maximum at that point, okay? Similar to what we discussed before. So we can do a similar thing for a general n-dimensional quadratic form. There it gets a little more interesting. So let's do that. Okay, so if I should find the critical point of this, I need to write a differential of f. So the differential, this is my function. So this is an n-dimensional generalization of this function. Okay, it was just one-dimensional x, and if I have n-dimensional x, I will just compute the differential of that. X plus xta delta x plus bt delta x. So to compare it to what I was doing before. So this I can write as xtat, because this is a number, I can again transpose the entire thing, right? I'm going to write this as delta x, and I can put this here, xta, and here I will have bt times delta x. And if these two are differentials, then this has to be nothing else but the gradient of the function at my point x, which I'm looking at, okay? So let me rewrite this. Maybe I will rewrite it in a little bit nicer way. So if I I want to transpose this entire thing. So I will put there a plus at x plus b, the entire thing transposed delta x. Okay, so let me say that this is the gradient. Okay. So if the matrix A is symmetric, and that's what we assume here, because if A is not symmetric, we can just discard the anti-symmetric part and we will get the same thing. So we can just say that this is equivalent, that a plus at is just 2a, okay? So in that case, the gradient reduces to just 2ax plus b, okay? And if I want to find a critical point, then I need to set the gradient to 0, which means doing 2ax plus b equals 0, which means, of course, that 2ax equals minus b. And here I need to assume that A is invertible. Okay, if A was not invertible, things could get a little bit more complicated. So let's for now assume that A is invertible. It won't get that much complicated, but let's not worry about that right now. So the critical point is at 1/2 A inverse minus 1/2 A inverse B. Okay, and then I essentially what I want to do, I want to generalize all this stuff I did for the 1D case here. So far what I have done, I computed this, right? And then I want to generalize this trick to make the linear term btx go away, and I want to do in the matrix language. Okay, so we can do that. It's a little bit of an algebra, but it's not that bad. So basically the point is the same. I'm basically just generalizing to n dimensions. So I take this quadratic function btx plus c, and I will want to write it as something that, so okay, I established that this is the critical point. Okay, so what I'm gonna do, I will take the x, I will add, oh, I guess subtract the critical point A inverse B transpose, then I will hit it with A in the middle because it's a quadratic form matrix, and A inverse B again. Okay, so again, this is the same thing as I did in 1D before. Okay, I just said I will center it around the critical point. So here it's a little bit subtle, right? Because I have to keep the matrix in the middle, but the idea is exactly the same. So if I expand this, is this sort of clear? So what I'm doing here, I'm trying to rewrite this. So you can sort of put this aside. I'm trying to rewrite this so that the linear term goes away, and I can do that by putting this magical critical point here. Okay. So let me work it out, and then we will see what happened. So now I just apply distributivity and write it out. So I will get xtax, of course. Then I will have plus 1/2 B transpose A inverse transpose AX. That's the first term. Then I will get X transpose A 1/2 X transpose A inverse B. And the final term will be, you know what, let me just make it, no, well, I will write it properly, A inverse B transpose A 1/2 A inverse B. Okay, so just apply distributivity to this, that the A is always there. Everybody can follow that? I just did it all at the same, all at once. I hope that's okay. Okay, so now we can apply some simplification. So the A was symmetric, right? So this transpose doesn't matter. So this is going to be identity. This is also going to be identity. And this is just some constant, okay? So I'll just call this D, because the constant doesn't really matter when we are optimizing the function. It just shifts everything up or down. And what I care about are these terms which multiply x. So this is a constant. This is just like in the 1D case, just a constant term which doesn't really affect the optimization. So let's take a look. What do we have here? Here we have 1/2 of btx, and here we have 1/2 of xtb. That's here, right? If I put them together, I can, this is a number, so I can again transpose it, right? This is an incredibly useful trick, so you get used to it, I guess. So this is just btx. Okay? So altogether, if I should summarize it neatly here, this horrible term reduces to xtax plus btx plus some funny constant d. Okay, d is just a number. And that tells me how can I rewrite this thing using this expression. So if I do that, I will xtax plus btx plus c. So I will put there this term, That's actually my point. That's how I'll get rid of the linear term. X plus 1/2 inverse D. So that gives me this. Okay, so what I need to do now is add back C, that's what I had here, and get rid of the D. Okay, so this will just create some other constant. So that still doesn't matter, but what matters, I basically reduced it to this expression here. Okay, well, now comes the beautiful moment. Now I can introduce again the substitution, now vector substitution. And I'm gonna say that y is x plus 1/2 A inverse B. This function was f of x, right? So if I introduce a substitution, then f of y is gonna be nothing but y transpose a y plus some constant. Okay? And minimizing this function, that's quite easy, right? Because the matrix A exactly tells me what type of critical point this 1/2 A inverse B is. Okay? So just as we said before, if A is positive definite, we have a local minimum. In this case, actually global, because we are dealing with a quadratic function. If A is negative definite, then we have a maximum. And if A is indefinite, that's the case that could not happen in 1D. If A is indefinite, then we have a saddle. Then we have neither maximum nor minimum. Okay? And there is another, that's I guess what's summarized. I guess I can switch back to the slide. That's what's summarized here. And if, yeah, it's a little subtle when A is semi-definite, because then I can't even work with the inverse. So I will not do all the math there, but let me just explain you what happens there. Then you essentially can have multiple points which will be the same minimum. Okay, so the minimum won't be unique, but there will be like another, for example, line or an entire subspace of the minima. So just like a little subtlety you need to worry about sometimes. But let's not worry about that now. Okay? Yeah, so basically this is how you can optimize a general quadratic form. So first you find the critical point, and then you use the Hessian. In this case, the Hessian is directly the A, right? That's what the Hessian is in this case. And the definiteness of the Hessian tells you what type of local extremum, if any, the critical point is. Okay, so I guess this is like a baby version of optimization. In the slides, I even have like an optimization example. I think I will skip it now in the interest of time, but you can go through it later. But this is like a precursor to entire mathematical optimization discipline. Then you generalize it by giving it linear equalities. Then you can start throwing in linear inequalities, in which case you are in quadratic programming. There is another special subcase called linear programming. Have you heard these things before? There's a class about this, and it's something that's actually very useful. And this is I guess the tip of the iceberg there. It gets much more complicated when you start putting constraints on the x and so on. Any questions? Now there is one more thing I would like to explain, and let me start it with something we already know, that's least squares. So we talked about least squares before, right? So let me just quickly remind you. So like the prototypical example was if I was in plane and I had a bunch of points, each of them has some x and y coordinate, and I was looking for a best fit affine function, where the best fit was measured like this, right? I measured this distance, the vertical distance to my affine function. I squared these lengths, and I wanted to minimize them. This was my idea. That was the least squares idea, how to find the best fit affine function. Okay, we have done this before. What this reduces to is, again, a quadratic minimization problem. So minimizing ax minus b squared, right? I think what we talked about before was like if you cannot really solve the system exactly, then your next best shot is to just minimize the square norm of it. If you can't get it exactly to 0, the next best thing you can, well, how low can I get it, right? So That's the general view of that. And we can directly apply what we derived before for optimizing a quadratic form. So what you can do is you can take this. So this is just a dot product with itself, right? So here I just transpose the entire thing. So this is xtat minus bt. Then I multiply it out. So I get xtax. The ATA, that's an important type of matrix. You will be seeing more of it as we go on. And here we get the two terms which we then put together. So this is xtatb minus btax. The same idea, the same expansion as I did before. And these things, because they are numbers, you can transpose them and put them together, just as I did before. Okay. I guess that's what's elaborated on here. Again, I guess I'm using this trick a lot this lecture, so hopefully you will remember it. That a 1-by-1 matrix you can transpose and you're not changing anything. Okay. So here we can directly apply what we derived. So this is, well, I guess I just bring this up. Yeah, that works. So this is basically a special case of this, right, where the ATA plays the role of this A here, and the minus 2 BTA plays the role of this vector B here, okay? So if I just take this formula 1/2 A inverse B, I will get this. And it's interesting to see that this reduces exactly to the normal equations we have derived before when we talked about least squares. Remember when I was talking about the orthogonal projection of a subspace? It's led exactly to these normal equations, and this is a different way you can essentially get the same result. And it's even a little bit better because it tells you what, well, no, it's not better. It's exactly the same. The key thing here too is to realize that ATA is always positive definite if A has full column rank. So first of all, ATA is always at least positive semi-definite. How could we prove that? That ATA is always positive semi-definite? So we got two criteria, right, for positive definiteness. One of them involves sandwiching it with xt and x, taking quadratic form, and from that it's quite obvious. I guess I'll just do that. So you just take xt, a, t, a, x, okay, for any, you pick any x, you do this. Well, but this you can write just as ax transpose ax, which is just nothing but square norm of ax, and that's certainly greater or equal than 0. Okay. So from this, you immediately see that ATA is always at least positive semi-definite, okay, because of this inequality. Now, if you want to sharpen this inequality, you have to work a little bit. You have to assume, and we have to assume something. We have to assume that A has full column rank, okay? Because if A has full column rank, it means that A has trivial null space. That means, and if A has trivial null space, it means that if I have a non-zero x, then AX must be also non-zero. Okay, that's what trivial null space means. I hope you remember all this null space business. Well, that means that for every x non-zero, the xt, a, t, a, x, that's still the same as this, right? But if x is non-zero, this has to be strictly equal than 0, right? Because if this is not a 0 vector, there must be something squared, and something squared will be greater than 0. By something, I mean something non-zero. So yeah, so indeed ATA is positive definite, and if A has full column rank, then we can invert it, and we are back to the normal equations we discussed before. So that's not my point here. My point is now to generalize it to total least squares, which is more interesting version of the above. Okay, so here in the regular least squares, you could have objected to this way I was measuring the error. Okay, so if I had my data points at these locations here, I said that I was measuring the error by looking at the vertical distance from my best fit line. Okay, well, you might be objecting to it because maybe the better thing to do would be to actually doing a projection, orthogonal projection on the line. Okay, so instead of looking, because I don't really know what the slope of the line is going to be, right? So maybe it's better to be basically asking what is the distance of each of my data points from my best fit line. Okay, so the distance means that I'm doing orthogonal projection to my best fit line. So I'm looking for the best fit line such that the sum of these, what we can call errors, squared is minimized. Okay, so let me say that again because I'm trying to rush it now. So we can call this each of these guys, let me make this one, we can call this EI, and that's going to be the orthogonal projection of my datum onto this line. Okay, if this line has normal u hat, where u hat means that the norm of u is 1, okay, then to compute EI, all I need to do is to do a dot product. Okay, so if this is my PI here, so I have some data P1, P2, P3, and so on. So to compute the error, I just do the dot product of PI and my U. Okay, do you see that? The U is the vector I'm looking for, and I want to find such a unit vector such that after I take all these errors, all orthogonal projections of my data points onto the line I'm looking for, I will get as small as possible number. Okay, makes sense? At this point when everybody is already tired, but this is actually sort of cool and important, so let's try to digest it. So what we want to do here is to minimize these errors EI squared. Okay, this error is just the dot product of PI and U, so I can write it like this. And the key thing here is that there's a constraint that U hat must be unit. Okay, if I did not have that constraint there, what would happen? I would get a trivial solution. We just get U being equal to 0. Okay, because if I put there 0, then everything would get 0, and that would certainly be the optimum here, because this energy is bounded from 0, right? So it must be non-negative. But if I'm looking for a direction, that means that I can just put the constraint that the length of the vector is 1. Okay, and that will get rid of this problem. So how can we solve this, the total least squares problem? So we want to minimize this. So I can rewrite it like this. So there's nothing special going on. This is just the same thing twice. Here I transpose the same thing. And here the cool thing is, so this would be 1 by n vector. This would be n by 1 vector. This would be 1 by n and n by 1. So here I can write it as outer products. Okay, so this would be n by n matrices. I can do that because the dimensions match. Okay, and then I can plug the summation, put the summation inside, and get just some matrix A inside. Okay. So it turns out that what I'm left with is a minimization problem like this. So minimizing U hat transpose A U hat subject to U hat being norm 1. Okay. It's sort of easy to show that this matrix, well, of course it's symmetric, right? If you transpose it, you get the same thing. And it's also trivial to show that it's positive semi-definite. Exactly the same proof as before. Okay, if you hit it from the left with x, from the right with x, you will immediately see that this is a non-negative number. Okay? And the cool thing is that this is actually a non-convex optimization problem, because here we have a non-convex constraint. Okay, how would this look? How would this constraint u hat equal 1 look like in 2D? So it's a circle, right, in 2D. So that means that the vector is constrained to be on a unit circle. So that's really brutally non-convex. Okay. But this is one of the rare cases of non-convex problems which we can actually solve very efficiently. So that's, I guess that's why it's so important. And here is how we can do it. So yeah, so here's again what we need to do to minimize this quadratic form subject to this non-convex constraint. Essentially u hat being in a unit hypersphere in n dimensions. Okay. And here's what we are going to do to solve this. We will use the eigen decomposition of A, because A is a real symmetric matrix. That's what we established already. From the spectral decomposition theorem, we know we can find an orthonormal matrix of eigenvectors Q and a diagonal matrix of eigenvalues lambda. Because A was positive semi-definite, then the eigenvalues will be all greater or equal than 0. Okay, we're putting now everything together. So we can rewrite this like this, okay. And next, well, of course, this is again just Qt u hat the whole thing transposed, okay, which is begging for a substitution. We will use this substitution. We will say that v hat will be Q transpose u hat, okay. It's easy to see that if I required from u hat to be length 1, then the same thing then trivially applies to v hat, because the norm of v hat is the same as norm. I guess let me write it properly. Norm of v hat equals the norm of qt u hat, which equals the norm of u, right? So if I require u to be 1, I can as well require v to be 1, right? We had this property before, just the orthonormal. It's an orthonormal matrix, so it disappears in the norm. If you don't remember it, then protest, but I think that's simple. So what we can do, we can now use the substitution and simplify this. So if we do that, we are left with just a diagonal matrix. Okay. So that means that what we are minimizing is nothing but lambda 1 v1 squared and lambda 2 v2 squared. Okay. And I guess this should be subject to. Okay, well, subject to u hat squared equals 1, but that's equivalent to saying that v hat squared equals 1. That of course doesn't matter if I square it or not, right? Because 1 squared will just give me 1 back. Okay? So what we can say that we are optimizing this subject to v1 squared plus v2 squared equals 1. Okay? And at this point we are almost done. Maybe let me write it here. Because here I can just express the v2 squared from this equation. So I can just say this will be, let me get rid of the hats. I don't want to be writing hats all the time. Just assume the hats are always there. The hat was there just to emphasize that this is a unit length vector. So okay, so I express the v2 squared from this equation, and I plug it into here. So what I will get lambda 1 v1 squared plus lambda 2 1 minus v1 squared, okay, which is of course, if I put it together, so this will be lambda 1 minus lambda 2 v1 squared plus lambda 2, okay. So now I can assume some ordering of the eigenvalues, right? So let me, without loss of generality, let me, for example, assume that I numbered the eigenvalues such that lambda 1 is smaller than lambda 2, okay? You would have to be a little more careful if they were the same, but let's assume that's not the case to avoid some special cases. So let me assume that lambda 1 is the smaller one and lambda 2 is the bigger one. Okay, they are all real, so that's all cool. So that means that lambda 1 minus lambda 2 is going to be a negative number, right? Because lambda 1 was smaller, so I'm subtracting something bigger. And lambda 2 has to be at least 0, right? Because we said it's a positive semi-definite matrix. Okay. Well then, how do we minimize this? And we have the constraint, so now we have only one variable here, v1 squared, and we know that the v1 squared needs to be from interval 0 to 1, okay? Because if it wasn't, there would be no way of satisfying the norm of v equals 1 constraint, okay? So how do we minimize? Now that's really simple, right? Now we have to find v1 squared from interval 0, 1 such that this expression gets as small as possible. What do you think we should pick? That's simple. We want to make this as small as possible. Here we have a negative number, here we have a non-negative number, and we can go with v1 squared anywhere between 0 and 1. Where would you go if you wanted to make this as small as possible? If it was also like a price you have to pay. 1, yes, of course. So the solution is trivial. Solution is just v1 squared equals 1. Oops, v1 squared equals 1. And v2 squared, therefore from the substitution, that must be 0. Okay? So that means that trivial, the optimal v vector will be 1, 0. As simple as that. Okay? Now we can revert back from the substitution. So this v hat equals q to u. Well, that's just a different way of saying this is qv equals u, right? So if my optimal u is 1, 0, well then what's gonna happen? Then I will have q 1, 0 here. That's gonna be my u, my solution. And what is that? Well, q was the matrix of eigenvectors, okay? So that means that the u hat is nothing but the eigenvector corresponding to the largest eigenvalue. Let's get this right. This will be corresponding to lambda. Smallest eigenvalue, yes. So the u hat, the solution is, it's the eigenvector, smallest definitely. Actually, I think it's written here. I don't have to write it here. So the solution is that u hat is the eigenvector of A corresponding to the smallest eigenvalue. So that's exactly this direction. Interesting, if you wanted to flip it, if you wanted to say we don't want to minimize it, we want to maximize it. So instead of, if instead for this direction, you were actually looking for this direction here, I guess it should be still unit, right? So it'd be direction like this. What you would get by doing exactly the same exercise, you would find out that you need to be looking for the largest eigenvalue of A. Okay? And that's what's called essentially principal component analysis. And we will have more to say about that later. So I think that's a good conclusion, unless you have some questions. If not, then I'll let you go. Thank you for your attention.